This tape is about typical maintenance jobs done on a reciprocating air compressor cylinder and piston. We'll watch the worker disassemble an air compressor for inspection and repairs. Then the machine will be reassembled using replacement parts where necessary. In this segment of tape, the worker will prepare the compressor for disassembly by removing various inspection covers and the cylinder head. Let's join him. The workman installs a metal strap between the crankshaft hub and the machine. This strap will lock the moving parts of the compressor, preventing injury during the job. Now, there are several methods available to lock the machine, so check your facility procedures to see what method to use. After match marking the two inspection covers on this side of the machine, he starts to remove them. It's always best to match mark plates like this. When you reinstall them, there's less chance that they'll leak if they're installed the way they came off. The two inspection covers on this side are used to gain access to the piston rod packing, oil seals, and crosshead assembly. There are two more inspection covers just like them on the other side of the machine. Since this job is going to take some time, the worker wants to keep his parts in order. So by placing the screws in a plastic bag, there's less chance they'll get lost. This is particularly important if the job may be turned over to a second shift or if another worker will have to reinstall these covers. With the screws out, the cover can now be removed. While the workman completes removing the inspection covers, I want to stress the importance of locking the compressor. Even though the wheels have been taken off, the compressor could still move slightly while you're working. If your hands are in the way of the piston or other moving parts, you could be hurt. So lock the compressor. After the inspection covers are off, the next step is to remove the cylinder head. Let's rejoin the worker now as he rigs the head off the machine. The workman has installed a chain ball to support the head as he removes the nuts from the studs. Again, he's using a plastic bag to store the nuts. Now, the cylinder head has to be guided off straight and true to prevent damage to the studs. So he'll use the chain ball to support the head as he pulls it off the machine. Before going any further, however, he puts on his leather gloves. This is to protect his hands during the rigging operation. Cylinder heads will very often stick to their gasket seating surfaces. So to remove them, the head must be jacked off the cylinder using jacking studs. By installing a stud on each side of the head, he can tighten up evenly on each stud. This pushes the head off straight and prevents damage to the studs. Remember, the chain ball will support the head during this operation. As with any rigging operation, at least two men should be used, one to control the load and one to control the chain fall. So having his helpers stand by to ensure that the head is evenly supported, the workman starts to turn in on the jacking studs. You'll notice that he takes a few turns on one stud, then a few on the other one. Again, this keeps the movement of the head even. Once the studs extend all the way through the head, they'll come in contact with the end of the cylinder. At that point, the head will start to move off. As you can see, the head is starting to pull away now. Once it breaks free, the workman will be able to guide it off with the help of his assistant. Now, keeping an even strain on the chain fall, the workman gently slides the head off of the cylinder and moves it over to the table. Notice how he keeps his feet out from under the load in case it should fall. The workman is careful not to catch his fingers as the helper uses the chain fall to lower the head onto the table. Since the chain fall isn't needed for a while, the helper moves it out of the way. The next step is to install 2 eye bolts into threaded holes in the top of the piston. These eye bolts will perform 2 functions. First, they'll act as handles to allow the workman to turn the piston and piston rod so that he can unscrew it from the crosshead assembly. Also, he'll be able to use the eye bolts to pull the piston and piston rod free of the machine. The preliminary steps are completed now. With the cylinder head and inspection covers out of the way, the workman can remove the piston rod from the crosshead. But before we go on, stop the tape. Review the steps we've seen so far with your instructor. With the inspection covers and cylinder head removed, the workman can continue the disassembly. The next step is to remove the piston rod. Let's join the job in progress. Before removing the piston rod from the crosshead, one of the workmen uses a set of inside calipers to measure the distance between the piston rod and the nut. This measurement will be useful later on when reinstalling the rod into the crosshead. It should be at about the same position it is now. Next, the other workman loosens the set screw that locks the nut in place. Another set screw on the crosshead assembly is also loosened. This one is used to lock the threaded piston rod into the crosshead assembly. With both set screws loose, the piston rod nut can be loosened using an open-end wrench. Once the nut is broken free, the piston rod can be turned out of the crosshead. Now, while one workman watches the progress at the crosshead, the other worker turns the piston using the eye bolts he installed earlier. Since the piston is rigidly attached to the rod, the whole unit will turn. By using a threaded connection between the rod and the crosshead, the length of the piston rod can be adjusted. This is useful in setting the clearance and cylinder heads. The rod will have to be screwed out completely and then pulled free so that the workman can turn off the nut. Once the nut is turned off the rod, It's free to be pulled out of the machine from the cylinder head end. Let me take a moment to point out something. Even though the piston and rod can be removed separately, it's usually easier to take them out as a unit. Experience with the machines at your facility will help you determine which way is better. Let's rejoin the workman now. With the nut completely screwed off the piston rod, the helper will place it safely on the workbench. The nut will be stored with other parts below the bench. Now, before the rod is pulled out any further, the oil scraper seal has to be disassembled and supported. This particular type of seal is free to float on the piston rod. If the rod were pulled through the seal, the threaded portion of the rod could damage the sealing surfaces. To remove the seal, the cover plate housing has to come off. It's held in place by Allen screws. Using a little teamwork here makes the job go faster. So by working from both sides, the workmen remove the Allen screws. Now, as the last screw is removed, the very careful support housing to keep falling down the rod. Once the screw is out, the housing can be pushed up on the rod to get it out of the way and close the seals. As you can, seals are segmented and a spring is used to hold the pieces together. So after the rod is pulled out slightly, the helper gently eases the seals down the rod. The workmen take their time and use teamwork to perform this operation. Another pull allows the seals to be pushed up close to where the threaded portion begins. Now, as the seals are pulled onto the threaded portion, the helper is careful to support them. He wants to keep from scraping along the threaded rod. Then the workman pulls the rod free, and the seals are simply lifted off. To protect them, the helper wraps the seals in a clean, lint-free towel. Then they're placed in a plastic bag to keep all the pieces together. These seals are delicate, so extra care is required to prevent damage. The housing simply slips off the rod. With the seal package and housing all together, the helper places them safely under the workbench. Now he's ready to rig the piston and rod out of the compressor. The first step is to pull the piston as far out as possible without it coming completely out of the cylinder. Then the workman wraps a strap around the piston to support it while moving it to the workbench. A strap works well for this because it won't scratch or damage the piston. Also, the strap will tighten around the piston as it's lifted, holding it steady. The workman keeps the tension on the strap so it stays in place around the piston. Once the strap is attached to the chainfall, the helper gently lifts the piston enough to allow the workman to slide it out of the cylinder. As the piston clears the cylinder, the workman supports the weight by holding the end of the rod. Then the helper raises the piston to the height of the table. They're careful not to let it slip as they move it towards the table. Once it's over the table, they simply lower it in place and remove the rigging. Now that the piston is removed, the next step is to inspect the piston and cylinder. But before we go on, stop the tape and review the procedures for removing the piston and rod with your instructor. In the last segment, we saw the workman remove the piston and rod from the air compressor. The next step is to perform measurements on the cylinder and piston to determine if they're excessively worn. The workman has removed the old piston rings and is about to start measuring, so let's join him. Before taking any measurements, the workman wipes the piston clean. Dirt or other debris on the piston could cause an inaccurate measurement. He'll be using an outside micrometer for this particular step. What he's looking for are three things. Number one, what is the actual diameter of the piston? This will determine if the piston is worn. Number two, is the piston egg-shaped or out of round? This can be checked by taking two measurements 90 degrees apart. And number three, has the piston become tapered? To determine this, he'll take a second set of readings at the bottom of the piston. As he uses the micrometer, he relays the information to his helper, who records it. It's very important to write each reading down so that they can be compared with the manufacturer's specifications. They'll also be compared with the cylinder measurements later on. Now, if the piston is excessively worn, the instruction book could require the purchase of a new piston, or in some cases, the piston could be sent away to have a metal buildup done. This would restore the initial dimensions. The instruction book will tell you what to do. With all the piston readings recorded, the helper verifies them with a manufacturer's instruction book. In this case, all the readings are within tolerance. So no more work is required to be done on the piston. The next step is to measure the diameter of the cylinder. To do this, an inside micrometer is used. Now, before using the inside micrometer, the workman zeroes it. Then he verifies that it's accurate by checking it with his outside micrometer. Once he's satisfied that the inside mic is accurate, he won't have to check it again. So he can put the outside micrometer back in the plastic bag to keep it clean. Remember, micrometers are precision instruments and require special care. Before taking the measurements inside the cylinder, the workman wipes the cylinder clean of any excess oil or debris. A soft lint-free towel is used to avoid scratching the cylinder wall. Then, using
his inside micrometer, he sets it for his first reading. He'll take a total of 6 readings, 2 readings 90 degrees apart along 3 points of his at each and 2 in the center. The measurements of the cylinder will determine the actual diameter. Also, by taking 2 readings 90 degrees apart, the workman can detect if the cylinder is egg-shaped. Finally, by taking measurements at 3 points along the length of the cylinder, the workman can determine if the cylinder has developed a taper. Assuming the cylinder isn't egg-shaped or tapered, its diameter can be compared with the piston diameter to determine running clearance between the piston and the cylinder. As the workman completes his last reading at the far end of the cylinder, the helper compiles all the readings. They'll be compared with the manufacturer's specifications. Remember, he's looking for the actual diameter. He also wants to find out if the cylinder is egg-shaped or tapered. In this case, the cylinder diameter is within specifications and there are no abnormalities. Satisfied with that, the workman can fit the new piston rings into the cylinder to find out if they're the right size. The piston rings will compress as they're fitted into the cylinder wall, and the gap that's left in the ring must be a specific distance. If the gap is too small, the ring may bind when it gets hot and expands. If the gap is too large, it may allow excessive amounts of air to leak by the piston. So, using gloves to protect his hands, the workman fits the new ring into the cylinder wall. There's a small lip just inside the wall. The ring has to be forced over it to get it on the portion of the cylinder where it normally rides. Fitting the rings may require a little bit of force because they compress as they enter the wall. This is why gloves are used, to avoid cuts or scrapes while positioning the ring. Before the gap is measured, the workman must be sure that the ring is exactly perpendicular in the cylinder. If it were cocked slightly, it would give an inaccurate gap reading. So he uses a steel rule as a template to ensure that the ring is fitted equally in the cylinder on all sides. He checks at 4 points around the ring and then double checks the bottom of the ring where the gap is. Now he's ready to measure the gap. This particular type of ring uses an angle cut, so be very careful when using feeler gauges that you don't spread the gap apart during the measurement. The first blade doesn't fit, so he tries a combination of 2 blades to get just the right size. To check the thickness of the feeler gauges he's using, the workman uses an outside micrometer. You may have more blades than you think, so this is a good way to ensure that you know the thickness. After making the measurement, he relays the end to his helper. Then remove and repeat the procedure on the second ring. When the workman is satisfied that the piston and cylinder measurements are within specifications, he can start reassembly. But before we go on,
stop the tape and review this segment with your instructor.
In the last segment, the workman verified that the piston, cylinder, and replacement rings were all within specifications. Let's join him now as he prepares to reinstall the piston. The first step is to install the new rings on the piston. But before getting to the rings, the workman ensures that the grooves are clean. Dirt or debris in the ring grooves may prevent free movement of the rings. This could cause the piston to bind within the cylinder. To fit the new rings on, the workmen use thin sheets of metal shim stock. These sheets will help the ring slide over the piston into the groove. The sheets also protect the piston from being scratched by the ring. Now notice the workman makes sure the gap on each ring is over a piece of shim stock. This is where the sharpest edges are. The workman will use 3 sheets of metal to hold the first ring in the expanded position. This will allow them to slide it over the first groove. With the metal sheets in place, they gently slide the ring down the piston until it clears the first groove. The ring is left in that position to hold the shim stock in place while they install the second ring. It's important that the shim stock only covers the first groove and doesn't extend down over the second one. If it does, you'll have trouble setting the bottom ring in place. Next, the second ring is installed in a similar manner. With both rings in position, the bottom ring is gently slid off the shim stock and into the groove. Next, the shim stock is removed to release the second ring into its groove. Then the workman rotates the rings so the gaps are 180 degrees apart. This will prevent excessive leakage past the rings during operation. The piston rings should be free to slide within their grooves. A certain amount of side clearance is required between the groove and the ring to allow this. Now, having selected the proper size feeler gauge, he checks the rings at several points around the piston to make sure they're free to move. The specified clearance is very important. If the ring fits into the groove too tightly, it may bind in one position. That means it won't be able to expand and contract to conform to the shape of the cylinder. If the clearance were much too great, the ring would be too sloppy in the groove and could fall out. A ring falling out of a piston groove would result in severe damage to the cylinder and piston. Let's rejoin the workman now as he completes measuring the side clearance. The workman discovers that the clearance around both rings is within specifications. That is good. If the clearance were larger, it could indicate wear on the grooves. To verify his reading, he uses a micrometer and relays the information to his helper. It's a good idea to include clearance readings in the maintenance records. The next time an overhaul is done, you can compare your readings with the readings in the records. Any increases would indicate wear. Now, with the rings satisfactorily installed, the workman will compress them using a ring compressor. This device is used to compress the rings down to about the size of the cylinder. That way, the piston can be pushed in without the rings causing interference. Without this tool, it would be very difficult to get the rings into the cylinder wall. With the compressor placed over both rings, he tightens the set screw. Notice how the ring gap closes as the workman tightens the set screw. The band of metal compresses the rings to about the same size as the piston. When using a ring compressor, tighten it only enough to get the rings to about the same diameter as the piston. If you tighten it too much, you may not be able to slide it off when the time comes. It should complete the stuffing box. The rod is after the compressor used, seal the rod. The packing is held in a stuffing box
and is compressed by a packing follower. Once the workman has removed the two nuts, the packing follower simply lifts off. This exposes the packing for easy removal. Without the rod in the way, the workman simply places his fingers into the gland and pulls the packing out, one ring at a time. Always save the old packing so you'll know how many rings to put back in if the manufacturer doesn't give you guidelines. Also, if you don't have preformed packing, you can use the old packing as a guide for cutting the new. Now that all the packing has been removed and placed in a plastic bag, the workman sets it on the workbench. He'll compare it to the replacement packing later on. Now, before he installs the piston and rod, he's going to clean and inspect the packing gland. It's a lot easier to do this with the rod out of the machine. Using a clean, lint-free towel, the workman wipes the gland clean. There may have been some bits of packing or other deposits left behind. Then he uses a mirror to inspect the gland. It shouldn't be scratched or damaged in any way. If it is, the packing may not seal. Satisfied with the condition of the gland, the workman is now ready to install the piston and rod. But before he does this, he reinstalls the packing follower. This particular follower is a single-piece design and must be installed before the piston rod is replaced. The follower itself fits over the rod. To save himself time and trouble later, he installs the packing follower over the studs and hand tightens the nuts to hold it in place. This leaves him one less thing to have to slide over the rod. The machine will then be ready to accept the piston and rod. Before we see how to install the piston and rod, stop the tape and review what we've covered in this segment with your instructor. In the last segment, we saw the workman install new rings and remove the old packing from the stuffing box. Now he's ready to rig the piston into the machine. The workman and his helper are using a similar rigging setup as before to move the piston back into the machine. They'll also use the same cautions as before. They want to get the piston and rod close to the center of the cylinder before they try to insert it. While the helper controls the chain fall, the workman gently guides the piston rod through the packing gland and gets the piston started into the cylinder. Before going any further, the workman will remove the rigging strap. The piston's in far enough now to stay in place. With the rigging strap removed, the workman pushes the piston into the cylinder far enough to get the rings caught inside the cylinder wall. Notice how the ring compressor slides while the piston is inserted. Then he pulls the piston back out a little to allow him to remove the ring compressor. He's careful not to expose the rings as he does this. Using an Allen wrench, he loosens the ring compressor and simply slides it off the piston. The next step is to coordinate the insertion of the piston with the installation of the oil seals. The first piece to go on is the oil seal housing. He simply slips it over the rod and back as far as it will go. Next, he slides the oil seals themselves onto the rod, being careful not to damage the sealing surface. With all three pieces installed, the workman pushes the piston in slightly to allow the helper to slide the housing up onto the rod. The helper also moves the seals up close to the collar. The workman then pushes the rod in a little more to allow the helper to install the first seal. These seals are spring-loaded, so the helper has to stretch them out slightly. This expands the spring and allows the seal to slide up over the collar onto the rod. These are segmented seals. Care must be taken to prevent them from coming apart during installation. While the workman completes installing the second seal and housing, let me caution you to use care when installing these seals. If they should come apart during installation, refer to the manufacturer's instruction book for guidance on reassembly. There's only one way they'll go back together properly, and the manufacturer's instruction book will tell you how. Let's rejoin the workmen now as they finish installing the piston. With the seal package installed, the workman turns his attention to the inspection port at the crosshead assembly. The first thing he does is install the piston rod nut, but he doesn't put it on all the way. He wants the first few threads on the rod to be covered by the nut to protect them when the rod is pushed up to the crosshead assembly. The piston nut can now be turned up to about the same spot it was before disassembly. This will get it out of the way and allow the piston rod to be screwed in the crosshead. It will also get the rod back close to the same position as it was before. Again, the workman uses the eye bolts to turn the piston along with the rod. As he threads it into the crosshead assembly, his helper watches.
then signals him when he's reached the approximate set point. Next, the helper uses the calipers to get the piston, nut, and rod close to where they were before. Remember, this is to assure the piston rod length is pretty close to where it was. The rod is screwed in a little bit farther. The helper realizes that it's in just a little bit too far, so it's backed out a little bit. Then he checks it again. This time, the piston rod is just about where it was before disassembly. The final adjustment will be made after checking the clearances in the cylinder. Remember, the calipers were only used to approximate the proper rod length. To achieve the exact rod position, the clearance between the piston and cylinder heads has to be measured. But before we go on to that step, stop the tape and review this material with your instructor. You'll recall in the last segment, the piston and rod were installed close to their original positions. Now, to make the final checks, the workman is going to measure the piston clearance at each end of the cylinder. He's already removed 2 suction valves to gain access to the cylinder for his measurement. Now he completes the installation of the cylinder head. After checking the torque on the last 2 nuts, the workman is ready to remove the locking device from the compressor. You'll recall this locking device was installed at the beginning of the job to prevent rotation of the compressor. The next step will require the movement of the piston in the cylinder, so the locking device is removed at this time. This particular device connects the compressor housing and the crankshaft. After removing the nut and bolt from the metal strap, the workman simply turns it out of the way. Since the lock is removed, the workman calls his helper to hold the compressor crankshaft to keep it from rotating. The valve covers were installed to keep the openings clean when the suction valves were removed. So by simply lifting the covers off, he can use the access holes through the suction valves to make his measurements. A set of long feeler gauges will be used for this. The workman signals his helper to turn the crankshaft and move the piston as far as it will go towards one end of the cylinder. Then, using his feelers gauge, he measures the clearance between the piston and the cylinder head. It may take more than one try to get the right combination of blades. When the blades will just fit, he knows he has an accurate measurement. Then he uses a micrometer to measure the total thickness of the blades. Even though the blades are marked with their thicknesses, the most accurate method is to use a micrometer. You may miss a blade or two if you add them up separately. Once he has the thickness of this bunch of blades, he records it.
Next, the workman signals his helper to move the piston towards the head at the other end of the machine. He wants the piston as close to the head as it will go, and once he has it in place, he'll perform a similar measurement. After the workman records the second measurement, he'll add the two together. This will give him the total clearance. This total clearance has to be divided between the two ends of the cylinder to compensate for the expansion of the piston rod as it heats up during operation. Now, this particular air compressor is designed to have 2/3 of the total clearance at the cylinder head end and 1/3 of the total at the other end. Once the workman has computed the proper amount of clearance for both ends of the cylinder, he'll set the feeler gauge for one of the ends and start the adjustment procedure. Once again, he verifies the thickness of the feelers by using the outside micrometer. In this instance, the workman has chosen to set the feeler for the proper clearance at the cylinder head end of the machine. He knows from his measurements that the piston rod has to be shortened a slight bit to increase the clearance at the head end of the machine. So the workman directs his helper to move the crosshead assembly back to give them enough room to turn in on the rod. The rod has now been shortened slightly. To check the adjustment again, the workman has his helper move the piston as far as it will go against the cylinder head. And he checks the clearance with a feeler gauge. Satisfied that the clearance is within specifications, the piston rod nut can be locked in place. Then the helper moves the crosshead assembly back again so the workman can reach the nut and tighten it with a wrench. Before tightening the set screws on the piston rod and nut, the workman is going to double check the clearance between the piston and cylinder head. Once again, he signals his helper to move the piston as far as it will go towards the head. Then the workman inserts the preset feeler gauge to verify the clearance. He can now tighten the set screws to lock the piston rod in place. To gain access to the screws, the helper turns the crankshaft to align the crosshead with the inspection port. Remember, there are two set screws, one on the crosshead assembly and one on the piston rod nut. The workman tightens the set screws so the piston rod will stay in position and the clearance between the piston and the cylinder ends will be maintained. Next, the workman is going to determine if the rod is running true. That means it's not rising or falling as it moves back and forth. A dial indicator is used to make the measurement. The workman positions the dial indicator on the rod. When it's set, he zeroes the indicator, checks it to make sure that it returns to zero, then watches the dial as the helper moves the piston rod back and forth. Any deflection in the needle would indicate that the rod is rising or falling. If it were, the crosshead would have to be adjusted to level the rod. Since the piston rod is running level, no adjustments are necessary. Maintenance on the cylinder and the piston is now complete. After replacing the suction valve covers, the workman will lock the compressor again. Then he'll repack the piston rod and replace the inspection covers using new gaskets. That just about completes this tape on compressor cylinder maintenance. It's important to remember that other components, such as seals and packing, and other clearances,
such as piston rod length, were affected by this job. For that reason, you should have a good understanding of the entire machine before you start. Take the time to read the manufacturer's instruction book and clear up any questions before you turn the first nut. Stop the tape now, read your text, and review all this material with your instructor. In this module, we're going to take a look at some of the more common maintenance jobs you'll be performing on air compressors. The machines we're going to work on may not look exactly like the compressors at your facility. In fact, I'd be surprised if they did. Air compressors come in many shapes, sizes, and designs, each one fitting a particular need. The first type we'll be working on is a reciprocating air compressor, and we'll start the job by overhauling a discharge valve. This is an illustration of a typical reciprocating air compressor. As you can see, the discharge valves are mounted in the compressor cylinder. Most larger machines have several discharge valves feeding a common outlet pipe. The valve provides for airflow in the outward direction only. Let's take a closer look at a typical discharge valve. This valve is constructed the same way as the one we'll be working on. The first part I want to talk about is the seat. The seat is a finely machined plate. Contained within the seat are several slots. These slots allow air to pass through. The slots are covered by flexible strips of metal. These strips will bend to allow air to pass from the seat through the guard to the outlet of the compressor. Mated up against the seat is the guard. The guard is machined to be slightly concave, allowing the metal strips to bend until they come in contact with it. With the strips flexing against the guard, air passes through the slots and leaves the machine. Passing through both the seat and guard are machined bolts. These bolts are used to hold the seat and guard together. The compressor we're going to work on has been removed from the system and replaced by a new machine. After a major overhaul, it will be stored as a spare. Now, the first step in any job is to clean the work area before removing any parts. A wire brush is useful for removing rust or paint that could get into the internal parts of the air compressor. Let's join our workman now as he prepares to remove and inspect one of the discharge valves. By referring to the manufacturer's instruction manual, the workman knows the first step for removing the valve is to relieve the tension on a jam screw. The jam screw holds the valve firmly in the cylinder wall. Using a box end wrench, the workman removes the cap covering the jam screw. This cap also serves as a lock nut to hold the screw in place. With the cap removed, the tension is relieved by loosening the jam screw. This screw will have to be readjusted when the valve is reinstalled. By replacing the screw cap,
The threads are protected during the rest of the job. Next, the valve cover must be removed. To do this, the worker removes the 4 nuts holding it in place. Using a box end wrench for this step minimizes the chance of the wrench slipping or rounding off the nut. Notice how the tension is relieved evenly by loosening the nuts in a crisscross fashion. This technique should be used whenever you remove or install several nuts. With all the nuts loose, the worker backs them off by hand. He's careful not to spin them too fast. This could damage the threads. Supporting the cover with one hand, the workman removes the last nut and gently, very gently, guides the cover off. He's careful not to hit the studs, which could cause thread damage. With the cover removed, the valve yoke is exposed. This piece is used to apply the tension from the jam screw evenly around the valve. After loosening a set screw, the workman removes the yoke while supporting the valve. Next, he carefully eases the valve out of the opening. After setting the valve and yoke on the workbench, the workman inspects the opening. With the valve removed, he can see directly into the cylinder. Satisfied with the condition of the cylinder and piston, he replaces the valve cover to keep dirt or other foreign material out. This is a good practice to follow in any job that involves opening a system or component. In this case, the valve cover is available and ideally suited for the job. When installing it, the workman uses the same crisscross technique as he hand tightens the nuts. This is a good work habit to develop. Again, he's careful not to damage the stud threads by spinning the nuts on too fast. When you do this, be sure that the nuts are snug and evenly supporting the valve cover. Now that the machine is protected, the job is continued at the workbench. Before disassembling the valve, the workman checks its general condition. Excessive amounts of dirt may indicate a problem in the air intake filter. Next, he removes the gasket from the valve seat. A new gasket will be used for reinstallation. With the seat side down, the cotter pins are removed from the valve bolts and nuts. The workman makes sure the pin is as straight as possible before he tries to pull it out. The old cotter pins are discarded as they're removed. Used cotter pins are difficult to install and could break if they're bent and straightened several times. Make sure you have a firm grip on the pin before you try to pull it, and be sure to support the valve assembly. With the cotter pins removed, the workman then uses 2 wrenches to remove the valve nuts. You'll notice these nuts have several machine slots that will align with the hole drilled in the bolt. This is to allow installation of a new cotter pin. While removing the valve nuts, the workman keeps the valve assembly close to the bench. That way, if the wrenches should slip, the valve won't fall and be damaged. He also makes sure the wrenches are completely on the nut and bolt before trying to turn them. With the nuts removed, the workman carefully slides out the bolts. These bolts are machined and have a very tight fit with the opening of the valve assembly. Notice how he holds the 2 pieces together as he removes the bolts and washers. This keeps the strips from falling out. Turning the assembly so the guard side is down and the seat side is up, he lifts the seat off the guard. The valve strips will stay in the guard while he performs maintenance on the valve seat. Before we continue with the inspection and maintenance of the valve seat, I'd like you to stop the tape, discuss the procedure for valve removal and disassembly with your instructor. In the last segment, we saw the workman remove the discharge valve from the compressor and disassemble it at the workbench. With the valve guard and strips set aside, the next step is to clean and inspect the valve seat. Since a solvent will be used to clean the valve seat, protective equipment has to be worn. The worker uses a plastic face shield to cover his eyes and rubber gloves to keep the solvent off his hands. Most solvents will irritate hands to some degree, so it's always safest to keep them covered with rubber gloves. Make sure the gloves fit properly. If they're too tight, they could tear. Very large gloves could make the work clumsy. Since he'll be using a spray solvent, the workman has decided to use a tub. The tub will contain the extra spray as it splashes off the seat. This particular solvent is quick evaporating. That means it won't leave any residue on the valve seat that could present an explosion hazard when the valve is reinstalled. Also, the solvent has no chemicals to cause corrosion of the machine seating surface. After spraying, the worker uses a dry, clean, lint-free cloth to wipe off the dirt and solvent. By getting the valve seat as clean as possible, he'll be able to perform a more detailed inspection. He's looking for indentations where the strips might have worn the surface. He also looks for scratches or nicks, which could cause problems. The worker finds some small imperfections and decides to use a lapping block to remove them. But first, he removes the safety equipment and puts his hard hat back on. Lapping blocks are finely machined surfaces and should be protected when not in use. This one has a plastic cover. With the cover removed, the workman applies a small amount of fine grit lapping compound. He places little dabs of compound around the surface of the block. This will help it spread evenly over the entire surface. He also places a small amount of compound at various points on the valve seat. With the compound applied to both seat and block, he starts lapping. The technique he uses involves making small figure-8 patterns. As the compound spreads across the block, he makes continuously larger figure-8 patterns. It's a good idea to rotate the seat 90 degrees periodically. This allows for even lapping of the surface.
While the worker continues to lap the valve seat, I want to emphasize that he found very small imperfections. If he had discovered deep wear marks, a surface grinder would have been used to machine the seat smooth. In either case, remove as little metal as is necessary to recondition the seat. Now, let's return to our worker as he finishes lapping. You'll notice the lapping compound is spread over the entire block. The workman is now covering the full block surface with his figure eights. To keep the wear even on the lapping block, he rotates it 90 degrees periodically. With proper care, a lapping block will last many years before it has to be resurfaced. As he finishes the lapping job, he lightens the pressure on the valve seat and gently slides it off the block. Next, he carefully wipes most of the lapping compound off the surface. This lets him see if the nicks have been removed. If the imperfections are still there, he'd have to continue lapping, but he's satisfied that the seat appears to be smooth. In order to make sure, he'll remove the rest of the lapping compound. Since he'll be doing this using the same solvent as before, he puts his safety gear back on. He uses a new pair of gloves for cleanliness purposes. With his safety gear on, the workman sprays the seat thoroughly. He wants to be sure he washes off all the lapping compound. Any residual compound left on the valve could cause excessive wear between the valve seat and strips. When he's done with the solvent, he uses a clean cloth to wipe the seating surface. With the surface clean and dry, he inspects it for nicks. When he's satisfied that the surface is in good condition, he sets it on a dry towel and removes his protective equipment. Maintenance of the seat is now complete. But before the workman goes on to maintain the valve guard, the lapping block has to be cleaned. He replaces the cover to protect the block before he takes it away for cleaning. Now that the valve seat has been cleaned and resurfaced, it's ready for reassembly. The next job is to clean and inspect the guard. But before we go on, stop the tape and review the maintenance procedures on valve seats with your instructor. In the last segment, the workman resurfaced the valve seat by using a lapping block and compound. This altered the seating surface and means the old valve strips may not form a tight seal, so they'll have to be replaced by new ones. Before the workman cleans and inspects the guard, he removes the old valve strips. Remember, these will be replaced with new ones after he finishes inspecting the guard. He's going to use the same solvent as before to clean the guard, so he'll use the same safety equipment, rubber gloves and a face shield. Remember, the cleaning solution you use should be approved by your facility. Make sure it's fast evaporating and doesn't leave any residual deposits on the valve guard surfaces. Deposits could cause an explosion after the valve is reinstalled. The worker carefully cleans all surfaces of the valve guard. He wants to make sure that the air channels are clean. If excessive amounts of dirt build up in the channel, it could prevent the valve strips from seating properly. Then he uses clean, lint-free towels to wipe off the residue. Using another clean towel, He sets the guard down. Then he removes his safety equipment before doing the inspection. Now the worker will be inspecting for small shoulders or ridges that form in the concave slots of the guard. These shoulders form as a result of the valve strips repeatedly rising into the guard as the compressor is operating. If shoulders are found, they should be removed with a file to prevent the strips from binding. The worker is satisfied there are no shoulders, so he's ready to install the new strips. Be careful with new strips. Be sure that you keep them as clean as possible during installation, and make sure you use the proper replacement strips. They do vary from machine to machine. The workman handles the strips by the edges. He avoids touching the flat surfaces because any oil and dirt from his fingers could cause corrosion. He places the long ones in the center slots and the short ones in the outer, shorter slots. With the strips on the guard, the worker needs to find out if the side movements of the strips within the guard meet specifications. The strips should be able to slide back and forth a small amount so they don't bind. The worker uses a feeler gauge to make this measurement. With the proper blade size selected, he first uses it to position the strips within the slots. He's careful not to scratch the surface of the strips as he moves them around. With all strips properly positioned, the worker measures the end clearance on each of the strips. Once he's satisfied that the end clearances are within specifications, he's ready to make the direct lift measurements. Direct lift is the distance between the face of the guard and the flat surface of the valve strip. By placing a depth micrometer on the guard face, he can measure the distance from the face to the strip. He uses a data sheet to record his readings. He takes 2 readings on each strip, 1 at each end. Take care not to drive the depth micrometer down too hard because it might damage the valve strip. After finishing his measurements on the first strip, he'll go on to measure the others. It's important to record each measurement as you go along. Any further maintenance on the guard will be determined by the direct lift readings. If the measurement is slightly greater than the manufacturer's specifications, the face of the guard can be ground down. If the readings are too far out of specification, you may need a new guard. After the worker records his last reading, he puts away the depth micrometer. First, he wipes it off with a clean cloth. And then he puts it back in its case to keep it from getting damaged. Now the worker compares his data with the manufacturer's specifications. Remember, he'll use the readings to find out what to do. In this case, all readings are within specifications, so the worker can reinstall the valve seat on the guard. He takes care to ensure that he doesn't pinch any of the valve strips between the seat and guard. He then installs the valve bolts through the seat into the guard. The whole assembly is then turned over so that the guard side is up. This allows him to install the nuts. The worker installs a small copper washer. Then he carefully draws up the nuts, finger tight.
This holds the seat and guard together so the strips can't come out of their slots. As before, the worker uses the double wrench technique, this time to tighten the valve nuts. When tightening this type of nut, make sure that the slot in the nut lines up with a hole in the bolt. This allows you to install the cotter pin. The workman repeats the same procedure on the other side. To line up the nut with the hole, always tighten it until it lines up. Never loosen the nut to align it. The final step in reassembling the valve is to install new cotter pins. The worker simply places the cotter pin through the slot in the hole in the bolt. He turns up the long side with a pair of needle nose pliers to lock it in place. This procedure is repeated on the other side. Before we go on with the reinstallation of the valve in the compressor, I'd like you to stop the tape, review the information we've covered in this segment with your instructor. With the maintenance on the discharge valve done, the workman is ready to reinstall the valve on the air compressor. Let's join him. Before removing the protective cover from the opening, the worker makes sure the jam screw is out of the way. He doesn't want it to interfere while he installs the valve cover. He turns it a couple of times so that it's backed out enough, then reinstalls the jam screw cap. This protects the threads during valve reinstallation. Next, the worker removes the cover nuts. Notice he supports the cover as he does this. This is to make sure the cover doesn't fall as the last nut is removed. He's careful not to turn the nuts too fast to prevent galling of the threads. With the nuts off, he gently eases the cover off the studs. This exposes the opening. Now, before he installs the reconditioned valve, the workman inspects the opening and cleans the seating surfaces inside the cylinder wall. A clean, lint-free towel does the job. He also cleans the gasket seating surface on the outside of the cylinder where the cover gasket seals. If these surfaces aren't clean, the gasket may not seal properly, resulting in air leaks. Then he double-checks the internals to make sure they're ready to accept the reconditioned valve. Before installing the valve, he places a new gasket on the seat. The workman wants to ensure that he installs the valve seat first. This is because the air should flow from the seat to the guard and out of the cylinder. As he eases the valve into the cylinder wall, he makes sure the strips are parallel with the piston. A small pin on the side of the valve fits into a groove. This lets him know the valve is installed properly. Next, he places the yoke firmly against the assembly to hold it in place.
By turning the set screw slightly, he applies enough pressure to hold the yoke and seat assembly in place. With the yoke holding the valve in position, the workman removes the old gasket from the valve cover. He then wipes the gasket seating surface until it's clean before he installs a new gasket. With the gasket in place, the workman gently eases the valve cover onto the opening. He holds it in place as he installs the valve cover nuts. The cover should be firmly seated so the gasket will compress evenly. With all 4 nuts hand tight, he uses a wrench to tighten them in a crisscross pattern. With all the nuts tightened, the workman uses a torque wrench to even up the torque on each nut. This ensures that the gasket is compressed evenly and minimizes the chance of air leaks. When you use a torque wrench, continue to use the same crisscross tightening technique. After going around once, the workman double checks the torque on each of the nuts. This is a good practice because the torque may change each time another nut is tightened. Also, it will verify that you read the torque properly. With the cover installed, the next step is to remove the jam screw cap and gasket. As we saw earlier, the jam screw is used to force the valve against the seating surface of the cylinder wall. Using a small open-end wrench, the workman tightens the jam screw firmly. He then installs a new gasket. With the new gasket installed, the workman replaces the jam screw cap. Remember, the jam screw cap serves as a lock nut to hold the jam screw in place. After the final tightening of the jam screw cap, the job is complete. All the discharge valves on the compressor are maintained the same way. Next, we'll watch how the workman maintains a suction valve. But before we rejoin him, stop the tape and discuss the information in this segment with your instructor. The workman has completed the overhaul of all the discharge valves in the compressor. His next job is to remove and inspect the suction valve and unloader assemblies. Before we join him, let's see where the suction valves are located. Here's our air compressor again. There are several suction valves located around the cylinder. The unloader devices are attached to the suction valves. Let's take a closer look at these parts. This illustration shows an entire assembly. The suction valve is constructed the same way as the discharge valve. It sits in the cylinder wall like the discharge valve does. One major difference is that the suction valve is installed guard first. This allows air to flow past the seat and guard into the cylinder. Mounted on the suction valve is the unloader device. The unloader device is equipped with a set of metal fingers that fit into the air slots of the valve seat. When the unloader is actuated, these fingers pass through the slots in the valve seat and hold the metal strips open. With the strips open, air is free to flow in and out through the valve. Since no compression is occurring, the machine is unloaded. The workman is about to remove an unloader and valve assembly from the machine, so let's join him. The control air piping has already been removed from the compressor. Plastic caps have been installed on individual control pipes to protect the openings. After checking the instruction manual, the workman loosens the control air pipe packing stuffer. This stuffer compresses the packing around the pipe to form a tight seal. With the stuffer loose, the workman removes the control air pipe. As he unscrews the pipe from the unloader assembly and lifts it out of the valve cover, he's careful to pull the packing with it. Now, to cover and protect the opening, the workman installs a small pipe plug. The next step is to loosen the lock nut that holds the jam screw in place. This is a large nut, so the workman uses a slugging wrench. He's careful not to swing the wrench toward his body. With the lock nut loosened, the jam screw is backed off slightly. Remember, this jam screw will have to be readjusted when the assembly is installed. The last step is to remove the valve cover. Using a crisscross pattern, he loosens the nuts with a box end wrench. When all the nuts are loose, he removes them by hand. As he lifts the valve cover off, the workman is careful not to bang into the threads of the studs. With the unloader and valve assembly exposed, the whole assembly simply lifts out of the cylinder. Then the workman uses his flashlight to make a visual inspection of the cylinder and piston through the opening. Satisfied with their condition, he gently reinstalls the valve cover. Again, this is to protect the opening. He's careful not to damage the stud threads as he places the cover back on. With the cover on, he installs the valve cover nuts until they're finger tight. With the unloader valve opening safely covered, the workman is ready to disassemble the suction valve from the unloader assembly. After placing the unloader in the vise, he starts the valve removal by straightening the cotter pins. These cotter pins hold the valve nuts in place. Again, he tries to get the cotter pin as straight as possible before he tries to pull it out. Also, remember to discard the old cotter pins. Used pins are difficult to reinstall. As with the discharge valve, the workman uses a double wrench technique to loosen the valve nut and bolt. He's left the old gasket on the valve to protect its seating surface from any damage should the wrench slip. After removing the nut from the first bolt, he repeats the procedure on the second side. Again, he's careful to turn the nuts off slowly. This keeps the threads from becoming galled. Now, rather than lifting the valve off at this point, the workman's decided to remove the nuts from the unloader's side. This leaves the bolts holding the two halves of the valve together until he gets it on the workbench. Remember, he doesn't want the strips to fall out of the valve. With the second unloader nut removed, he'll lift the valve and the bolts free of the unloader mechanism, exposing the fingers of the unloader. The workman performs the same inspections and maintenance on the suction valve as he did on the discharge valve. You'll remember, the major steps were to separate the seat and guard, clean and inspect the seat, then lap the seat if necessary. Next, the workman cleans and inspects the guard, then installs and measures the new valve strips. Finally, the reconditioned valve is properly installed on the unloader. With the suction valve maintenance complete, the workman is going to check the operation of the unloader. But before we go on, stop the tape and review this segment with your instructor. In this segment, we're going to watch the workman check the operation of the unloader. Anytime suction valve strips are replaced, you should verify that the unloader fingers will completely open each metal strip. Let's see how that's done. To test the operation of the unloader, the workman is going to remove the spring underneath the unloader piston. The spring makes it difficult to move the piston by hand. So by removing it, the piston and unloader fingers will move more easily. The first thing he does is to remove the cylinder cover. The cover is attached with 4 bolts that thread into a flange on the cylinder. The workman uses a crisscross sequence to loosen the cover evenly. This is especially important here because the unloader spring and piston push up on the cover. With all bolts loose and tension relieved, the mechanism is placed upright. The workman can then completely screw out the bolts. Notice how the cover has been pushed up slightly by the spring. With the last bolt removed, the cylinder cap simply lifts off. To remove the piston, he uses a small jacking bolt. This allows him to pull the piston up and out of the cylinder. Notice the 2 small rings on the piston. These rings form a seal between the cylinder wall and the piston. With the piston removed, the workman removes the spring retainer bolt. This bolt, along with its washer, holds the spring in place underneath the piston. When the bolt is removed, the spring is free to be lifted out. Before he reinstalls the piston, he puts the spring retainer bolt and washer back in place. This is important because the bottom of the piston sits on top of the bolt. To reinstall the piston, the workman will use a ring compressor. A ring compressor holds the rings close to the piston and allows it to slide into the cylinder. Now, the edges of the ring compressor are very thin and sharp, so he's going to use a pair of leather gloves to protect his hands. Next, he gently tightens the ring compressor evenly around the piston. Then he pushes the piston out slightly to get it started, sets it on the cylinder, and gently pushes it into the cylinder. With the piston installed, the worker no longer needs the gloves. His next step is to remove the small jacking bolt that he threaded into the top of the piston. With the jacking bolt off, the unloader mechanism is ready to be tested. He uses a vise to hold it securely. To perform the test, the workman places a small piece of paper between the valve strip and guard. This particular test requires the assistance of a helper. As the helper depresses the piston, the worker checks to see that the paper is captured between the strip and the guard. The helper then releases the piston and the paper is removed to check the next strip. Each valve strip is checked this way to make sure the unloader fingers are effectively holding them open. If any strip doesn't open enough to hold the paper, check all the unloader fingers. They should all be of equal length. To find out if they are, remove the valve and place a straight edge across the fingers. Then file the longer fingers down until they're all the same length. After the workman determines that the last strip is okay, he removes the paper from the valve. The unloader is then taken out of the vise. The spring is replaced by reversing the removal procedure. First, the piston is removed. Then the spring retainer bolt and washer. Next, the spring is installed, followed by the retainer bolt and washer. A ring compressor is used to insert the piston. Finally, the cylinder cap is installed. With the unloader and suction valve reassembled, the workman is ready to put them back on the air compressor. But before we continue, stop the tape and review this material with your instructor. In this segment, we're going to see how to reinstall the suction valve and unloader assembly. Let's join the workman. His first step is to remove the suction valve cover. Remember, the cover was installed at the beginning of the job to keep the opening into the cylinder clean. Dirt or foreign objects entering the cylinder could cause damage. Also, it's difficult to retrieve anything that might fall in. So always cover openings before you leave them unattended. Using a flashlight, the workman inspects the opening. He wants to make sure the gasket seating surface in the cylinder wall is clean and free of debris. Satisfied that it is, he installs a new gasket. This gasket forms a seal between the valve assembly and the cylinder. With the gasket installed, the valve is set into place. It should seat firmly on the gasket. Also, the pins on the valve assembly should align with the slot in the cylinder wall. Before he reinstalls the valve cover, the workman needs to remove the old gasket and packing and clean the cover. While the worker prepares the valve cover for installation, let me take a moment to stress some important points. Most gaskets won't seal properly if they're used more than once. So before you start the job, make sure you have new gaskets available. The same is true for packing. Always replace the old packing. Finally, if they are to be sealed with packing or gaskets, make sure all surfaces are clean. Otherwise, you may have leakage. Let's get back to the job now. With the valve cover cleaned and ready for installation, the worker installs a new gasket. This gasket seals the cover as it sits on the cylinder. He carefully installs the cover, making sure he doesn't damage the stud threads. Next, he turns the cover nuts on finger tight, uses his box end wrench to complete the tightening, and then checks the torque on each nut with a torque wrench. With the cover installed, the worker can install the jam screw and lock nut. First, he backs the lock nut up onto the screw. Then, he carefully turns the jam screw into the valve cover. Remember, the jam screw forces the valve and unloader assembly against the cylinder wall to seal it. The worker uses a box end wrench to finish tightening the jam screw. Before the workman tightens the lock nut, he's going to install a small strip of packing under it. There's a concave surface under the nut that accepts the packing. The packing seals the opening in the cap where the jam screw is threaded in. He uses a small piece of wood to position the packing. He tightens the lock nut finger tight. And using his slugging wrench, the workman completes tightening the lock nut. The last piece to go in is the control air pipe. So the worker removes the small pipe plug he used to cover the opening. Then he removes the old packing. Using a towel, he wipes the surface clean. Remember, the area on the pipe where the packing will seal has to be clean if you expect it to seal and not leak. Next, the worker places the control air pipe through the opening in the jam screw. He threads it into the unloader cylinder cap, then uses a small wrench to complete the tightening. With the control air pipe installed, the last step is to place new packing around the pipe where it penetrates the jam screw. Once again, a small strip of wood is useful for positioning the packing without damaging the sealing surfaces. The workman cut this piece of packing by using the old piece as a measuring guide. To position the packing, he winds it around the control air pipe as he pushes it into place. Now he's ready to start tightening the stuffer. To tighten the stuffer, he has to apply a little bit of inward force to compress the packing as he threads it into the jam screw. Finally, he tightens it a few turns to complete the job. Keep in mind that the packing stuffer may have to be adjusted when the compressor is placed in service again. We've covered a lot of material up to this point. So stop the tape and have a review with your instructor.
If you look around any industrial facility, you'll see all sorts of rotating machinery. This equipment is important. So it's our job to keep it operating efficiently for as long as possible. Rather than dealing with each component separately, this program is going to cover a job that's common to most rotating machines: alignment. Let me back up a little bit to explain what I mean by alignment. Most rotating machines, like these, for instance, are made up of two basic parts: a driver component, in this case a motor, and a driven component, in this case the generator. The two components are connected by a coupling. We perform an alignment in order to position the two components so that they rotate smoothly together. When two rotating shafts are coupled together in perfect alignment, they'll turn as if they were one shaft. That's the ideal situation, and it's very difficult to do. But the closer you can come to perfect alignment, the better it is for the machines and coupling. Even though most couplings are flexible enough to handle small amounts of misalignment, they'll last a lot longer if you approach perfect alignment. So what's perfect alignment? To understand that, I think it's easier to find the answer by asking the question in reverse. What's misalignment? Here's a drawing of a pump and a motor. I'll use it to explain what I mean by misalignment. Let's assume for now that the components are in perfect alignment. Now suppose we position the motor like this. We now have misalignment. It's called angular misalignment because one shaft is at an angle to the other. This, of course, is exaggerated, but it gives you the idea of what angular misalignment is. Let's remove the angular misalignment now so I can show you the other type you may find. Okay, now let's position the motor like this. What we have here is called parallel misalignment, or offset. The name comes from the fact that although the two shafts are parallel to one another, they are offset so that the centers of the shafts don't meet. For that reason, parallel misalignment is sometimes referred to as offset. Those are the two types of misalignment: angular and parallel. When no angular or parallel misalignment is present, you'll have perfect alignment. So the trick to an alignment job is to determine whether or not misalignment exists. Then you have to determine what type it is and correct it. Before we go on, let's review what we've covered so far. When two shafts in perfect alignment are coupled together, they'll turn smoothly. Angular misalignment exists when one shaft is at an angle to the other. Parallel misalignment exists when the two shafts are offset. Stop the tape now. Now that we know that two types of alignment exist, let's go a little deeper. Misalignment is measured in two planes: vertical and horizontal. Let's take them one at a time while I explain the difference. The drawing we're looking at shows the pump and motor from a side view. From this point, any misalignment found would be in the vertical plane. Let me show you what I mean. If we introduce some angular misalignment, it's caused by raising or lowering one end of the motor. This creates the angle between the shafts. So this is called vertical angular misalignment. Anytime one shaft is tilted up or down in relation to the other shaft, vertical angular misalignment exists. Let's realign the shaft and look at the other alignment problem that can occur in the vertical plane. When parallel misalignment occurs in this plane, it means that one shaft will be higher, like this, or lower than the other shaft, like this.
So this is called vertical parallel misalignment.
So when viewing machinery from the side, you can detect misalignment in the vertical plane. It could be angular or parallel. In a lot of cases, you'll find a combination of both. In other words, the shafts will be at an angle to one another and offset. The same problems can occur in the horizontal plane. Let me show you. Here's the same pump and motor combination. This time, however, we're looking at them from a top view. That way, we'll be able to see horizontal or side-to-side misalignments. If one shaft is shifted to create an angle like this, or like this, we have angular misalignment in the horizontal plane, or simply horizontal angular misalignment. Let's get back in alignment now and see the other type. If the whole motor is shifted one way, like this, or the other way, like this, we have horizontal parallel misalignment. And of course, you may find a combination of angular and parallel misalignment in the horizontal plane. If we put together everything we've seen so far, what have we learned? Well, there are two types of misalignment, angular and parallel. And there are two planes for misalignment to occur in, vertical and horizontal. So we end up with four types of misalignment to contend with: vertical angular, vertical parallel, horizontal angular, and horizontal parallel. And you may also find different combinations of the four types. Before you review this material with your instructor, I'd like to show you the four examples one more time. Stop the tape. We've identified that two types of misalignment exist, angular and parallel. And we also know that these misalignments can occur in two planes, vertical and horizontal. Now, I think the next step is to spend some time discussing the methods you'll use for detecting various misalignment conditions. Here's the pump and motor combination, and we're looking at them from a side view. Now, suppose we assume they're in perfect alignment right now. If the motor tilted like this, what type of misalignment would we have? If you're thinking vertical angular, you're right. Notice the angle that has formed between the two shafts when looking at them from a side view. One way of detecting this would be to measure the distance between the coupling halves at the top and at the bottom. If they're not equal, you have angular misalignment. In this case, the distance at the top is greater than the distance at the bottom. So we know we have a problem. There are a number of ways to make the measurement. A thickness gauge like this one can be used to get a pretty accurate reading. By fitting the gauge between the coupling halves, you can detect variations in the distance between them. There's a more accurate method, however, the dial indicator. The dial will give you a very accurate indication of any variations in distance between the two coupling halves. We'll spend a lot of time using it later on, so I won't go into detail at this point. What I do want you to remember now is that angular misalignment is detected by measuring variations in the distance between the coupling halves. In the example we saw, vertical angular was shown. Horizontal angular is detected in the same way, except you look for variations in distance from one side to the other rather than from top to bottom. How about parallel misalignment? Let's go back to a drawing while we discuss it. Once again, we're looking at the pump and motor from the side view. Now let's raise the whole motor to introduce some parallel misalignment in the vertical plane. How do we detect this? We make offset between the outer diameters of the two coupling halves. In other words, these distances
indicate how much too high the motor is.
The same measurement can be used to determine horizontal or side-to-side offset. How do you make this measurement? Well, one way to determine that some amount of offset exists is to use a straight edge. By placing the straight edge across the two coupling halves, a flashlight can be used to check for a gap, indicating some offset. While that method will give you an indication of whether or not parallel misalignment exists, it's not a very accurate way of determining how much offset or misalignment you have. In a little while, you'll see how the dial indicator is used to make very accurate measurements of offset. But for now, just remember, parallel misalignment is detected by measuring offset between the two coupling halves. It can be measured top to bottom for vertical parallel and side to side for horizontal parallel. Let's review now. Angular misalignment is detected by measuring the distance between the coupling halves. Variations from top to bottom mean vertical angular. Side-to-side variations mean horizontal angular. Parallel misalignment can be detected by measuring the offset between the coupling halves. High or low offset means vertical parallel. Side-to-side offset means horizontal parallel. In the next segment, we'll look at the dial indicator in more detail. But for now, stop the tape. Now let's move on to discuss the dial indicator as an alignment instrument. As you know, the dial indicator uses a plunger to move the needle on the dial. Inward motion of the plunger causes a clockwise needle movement for an increased reading on the dial. Outward motion of the plunger causes counterclockwise needle movement for decreased reading on the dial. By properly mounting the dial on the shafts, you can use the motion of the plunger to measure misalignments. There's a lot to see concerning this procedure, and I think it'll be easier to understand if we watch an alignment job. We're going to pick up a job that has already progressed through some of the preliminary steps. Things like routine coupling maintenance and rough alignment using a feeler gauge and straight edge have already been done. It has also been verified that both shafts and couplings are round by using standard run-out procedures. Now you're ready to get started on the final alignment using dial indicators. There are several ways to mount the dials. The one I like to use involves an alignment kit. Let's look at a mock-up so you can see how it works. Think of these two pipes as the shafts of the machines we're aligning. The union between them represents a coupling. This kit allows you to mount the dials on the shaft rather than directly on the coupling. This has a couple of advantages. First of all, you don't have to be concerned with the many shapes and sizes of couplings. Secondly, you can bolt the coupling together so both shafts between them represents a coupling. Pipes as the shafts of the machines we're aligning. The union between them represents a coupling. This kit allows you to mount the dials on the shaft rather than directly on the coupling. This has a couple of advantages. First of all, you don't have to be concerned with the many shapes and sizes of couplings. Secondly, you can bolt the coupling together so both shafts of couplings. Secondly, you can bolt the coupling together so both shafts